Good afternoon. My name is Ken Davis. I'm from Penn State University. I'm here to describe the Atmospheric Carbon and Transport America, or ACT America program. This is a NASA Earth Venture suborbital mission. I'm the principal investigator. Many people involved. Throughout this talk, I will try to bring up the image of a cup of coffee to help explain what we're doing. Imagine cream dropping into a cup of coffee and then stirring it. Our objective is to understand the sources and sinks of greenhouse gases in the atmosphere. If we could move on. We know that the coffee is getting lighter. That is, human activity is adding greenhouse gases to the atmosphere. And here's a couple examples of that. These are the measurements started by Dave Keeling of CO2 at Mauna Loa. You only have to look at one spot in the cup of coffee to know that it's getting lighter, right? Concentrations are going up. We know there's a net source. We know this for methane as well. What we don't know as well is what are the location and magnitudes of the biological sources and sinks of CO2. We know the anthropogenic emissions fairly well. The biological part of the story is not so well understood. And we don't know the magnitude of most of the methane sources. We know the net, but if you ask any individual source in the system, we have large uncertainty bounds. So we're trying to improve our knowledge of these fluxes. If you know something about the spatial structure of the greenhouse gases, or to go back to the coffee cup, if I could measure the creaminess at one point and the creaminess at another point, the difference would tell me something about where the cream is coming from and maybe what its source strength is. So this is what we try to do with greenhouse gases in the atmosphere. And here's one example, classic paper from Peter Tons in 1990, where we measured carbon dioxide in the atmosphere from the South Pole to the North Pole. That's the solid line, and compared that to numerical models that included all the sources and sinks that we knew of. And the result was that the gradient from pole to pole with the sources and sinks that we knew was greater than what we measured. So the inference was there's a large sink of CO2 in the northern hemisphere biosphere, that if you include that, you can bring this into agreement. Similarly, we've looked at CO2 over the Corn Belt. And you see that over corn, the concentrations in summer are 10 parts per million lower than the rest of the continent. So there's a sink there. We can infer these sinks if we understand the atmospheric transport, which looks like this. Could we go to the next slide and put this movie on? It starts green, I think, for some reason. There is a movie there. This is from NASA Goddard Space Flight Center. It'll turn back to those nice colors in a minute. I'm not sure why it started green. I think that was my problem. But this is showing the weather systems swirling CO2 through the atmosphere. This is North America. The triangles are where we have measurements that are continuous. And you see weather systems stirring this up. So the cream in the coffee doesn't diffuse gradually. It's stirred in this chaotic motion. And to know if we have this mixing right, we need observations. And we don't currently have a network of observations we can use to make the equivalent of a CO2 weather map. So this is what we're addressing with aircraft. So we have flown 73 research flights in 3 different seasons. We have 2 more campaigns to go across the whole eastern United States, which, as you saw, was a hotspot for both weather and sources and sinks of greenhouse gases. So that's why we're flying in this location. What have we learned so far? For example, we have seen that, just like the movie, when there are frontal systems coming through, there's a low pressure system in Oklahoma with a cold front and a dry line with warm flow and cold flow, you see huge gradients in methane and CO2 organized by those frontal boundaries, just like the movie showed, which is great. We can use this information to infer the sources and sinks. We also see that if you look across these frontal boundaries during a season, that the gradient is always the same. We always saw low CO2 in the cold air, high CO2 in the warm air in the summer of 2016. It flips sign in the winter. The other thing that we've done then is start to compare this to the numerical modeling systems we use to interpret those long-term observations to infer the sources and sinks. And the first message so far is they're not bad. And this is a good place to start. So this is an example of a numerical simulation of a front, longitude, altitude. These are the aircraft measurements, and the background is the simulation. So at first cut, we do a decent job of reproducing the structure that we measure in the atmosphere, which is good news for our inference of these sources and sinks. This is the same weather system. You can see there was a front here across Nebraska, and we flew this path. This is the side view. This is the top view. You can see the frontal boundary, as in the cold front there. Similar to the movie, of course, we can't make a movie of the measurements because the measurements aren't everywhere all the time. And that is the aircraft data. And it's not exactly right, but it's close. So in the future, we have to do quantitative model data comparison with all the flights across all the seasons, composite the performance of the models, look for the biases and the errors, reduce the errors, come back with an improved set of numerical modeling systems to then interpret the data, learn about the sources and sinks of CO2 and methane in the atmosphere. That's my story.